All right, here I am, and I am about to try my best to explain to you electronic configuration via YouTube. I highly recommend that you take a look at some other videos, maybe online, about this. This is not a particularly challenging concept, but I think I'm going to struggle to explain it to you just via this video. I think I'm much better at explaining this with my hands and in front of you, but I'm going to do the best I can until I see you guys in person. So, we have been talking about electrons. So the last thing that we covered was the Rydberg equation, where we talked about how we had an electron and we could promote it, or we could let it relax down, and we talked about those energy shells that electron can go into. Well, every atom has those particular energy shells. And so when we are talking about an atom of hydrogen, it's very easy. One proton, one electron, no big deal. But when we're talking about an atom of lithium, iron, any of the other ones, we have many electrons. And we need to account for where those electrons lie, close to the nucleus, far from the nucleus, what other electrons are around that particular one. We need to know what is the location of every electron in the atom. If we know about the electrons in the atom, then we can predict the atom's reactivity. So we're going to do the full electronic configuration for many different electrons, many different atoms, and for all of the electrons within that atom. So first I have to give you some definitions. So the first definition that I'm going to give you is the energy shell. The shell of where the electron lives. This is very similar to what we've done previously in the Rydberg equation. The shell where the electron lives is given with the symbol of lowercase n. It gets a whole number coefficient. This will make more sense to you as I go on, but I'm going to give you the definitions first. So it's a whole number coefficient, and it corresponds to distance from the nucleus. When n equals 1, that is the ground state that is closest to the nucleus. So as you get further and further away, n equals 2, 3, 4, etc., you get further and further away from the nucleus. After this shell of where those electrons live, you get what's known as the subshell. The subshell is based on the shape of what that particular location where the electron lives looks like. So it's based on the shape of it. Now remember, I told you that we can kind of assume that an atom is like, the nucleus in the middle, and then we have electrons orbiting around it. And I told you that was a lie. Well, this is where things get a little bit muddy, because now I can't lie to you as much. And I'm going to tell you that where the electron lies is not really just a sphere. It's not just an orbit. It has different shapes to it. So the subshell is based on the shape. There are 4 different subshells. The S subshell is shaped like a sphere. Okay, it's in 3 dimensions. We're not just in 2 dimensions. I know it looks like a circle, but it's a sphere. So S equals sphere. You need to memorize that. S, sphere. P is the next subshell. P is shaped like a dumbbell, with the nucleus in the middle, and then you have a location where you can find an electron above and an location where you can find an electron below. So P, dumbbell. Got to memorize. D is the next subshell. That, for the most part, is shaped like a cloverleaf. There's one that's a little bit more complicated than a cloverleaf. But you can see as we go up in shapes, things get more and more complicated. Like going from a sphere to a dumbbell, it's like you take that sphere and you pinch it, and that's how you get a dumbbell. You take that dumbbell and you pinch it, and you get a cloverleaf. These things are very technically called nodes. We're increasing the number of nodes. It doesn't matter. All that matters is that S is sphere, P is dumbbell, D is a cloverleaf, and F is more complicated. So those are the subshells. Those are the where the electron lives looks like. What is the shape of where it lives. And then each one of these subshells is broken down even further into orbitals. And that's really where the electron can go in singly first before it pairs. You might have heard that before. It's where the electron can get up with a teammate, and you can't have more than 2 per orbital. Okay, so we have the shell, whole number, n equals 1, 2, 3. The subshell is the shape, S is a sphere, P is a dumbbell, D is a cloverleaf, F is complex. And then the orbital is really the location in which it lives, kind of like the room in the house where the electron lives. You can't have more than 2 electrons per orbital. All right, so let's find my cursor and let's do this electron count. Every orbital can hold a maximum number of 2 electrons. So I know that this looks like something you're going to have to memorize. You won't actually have to. It'll fall out. It'll be really straightforward. But an S subshell that is shaped like a sphere has 1 possible orbital. So it can hold a grand total of 2 electrons. It has 1 place for those electrons to live. 1 electron can go in singly first, and the next one can pair up with it. So an S subshell has 1 possible orbital. Every orbital contains 2 electrons, so 2 electrons can live there. Goes in singly first before it pairs. A P subshell, let me switch colors. A P subshell has 3 possible orbitals. So it has 3 possible locations for electrons to live. Each location can hold 2 electrons. That means that you can have a grand total of 6 electrons in there. Those electrons go in singly first before they pair. So a P subshell, dumbbell-shaped subshell, can hold up to 6 electrons. D subshell can hold up to 5 orbitals. It has 5 possible locations. 1, 2, 3, 4, 5 possible locations. Each location can hold up to 2 electrons. They go in singly first before they pair. So the total number of electrons that a D subshell can hold is 10. And last but certainly not least, we have an F subshell that contains 7 orbitals. 1, 2, 3, 4, 5, 6, 7. So there's like 7 rooms in the house where an F electron can live. The electrons go in singly first before they pair. So an F subshell with 7 orbitals can hold up to a grand total of 14 electrons. All right. Far so good. This is exactly what I would say in class. Again, this seems like it's real complicated, but I'm going to show you the shortcut using the periodic table, how you can give the full electronic configuration for any element just using the periodic table. So all you need to remember is S, P, D, and F, I promise. Now here is the periodic table. So I went purple, green, blue, orange, purple. Okay, these 2 rows of the periodic table are the purple ones. Then we got green. Over here are the green ones. Purple, green. Then I went blue. And, oh, all these colors are horrible for orange. That's okay, I don't use these ones that much. Orange. All right, so the first thing I'm going to do when I explain this periodic table that I've got here is I'm going to move helium over. I've said before, you guys, in class that like hydrogen and helium are kind of a little bit obnoxious. Hydrogen is not a metal, but it's in that group 1 with the rest of the alkali metals, and so it's like, hydrogen kind of doesn't belong over there. Here's a case where helium is actually, and I've told you that hydrogen has something in common with the halogens in group 7. Helium is also one of these ones that doesn't really fit. So we're actually going to take helium, and for our purposes, we're going to move helium right on over to here. All right. The other thing I'm going to do on this periodic table before I go any further is I'm going to number these. So this is the first period of the periodic table. Hydrogen and helium are in period 1. Lithium and beryllium, and then straight over to boron through neon. That's group 2. Group 3 is sodium and magnesium, and then over to aluminum through argon. And then group 4 is potassium and calcium. Okay, so we've got our periods of the periodic table numbered. We've moved helium over. And now those colors. The purple group on the periodic table is the S block. So the S block, S is a sphere. It has one possible, the S subshell has one orbital. Each orbital can contain 2 electrons, so it can contain a maximum of 2. And how many atoms are there per period? 2. So the periodic table tells you 2 electrons can fit into an S orbital. As long as you remember that these first 2 columns are the S block. S orbitals can fit 2 electrons. Coming on over here to the P block is the green. The P block has 3 orbitals, and it can fit a grand total of 1, 2, 3, 4, 5, 6 electrons. So again, as long as you remember that green block is the P block, it can fit up to 6 electrons. You don't have to memorize anything. Moving on over, hopefully you guys can get what the pattern is going to be. This guy here is the D block. The D block has, the D subshell has 5 orbitals, can fit 10 electrons. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, 10 atoms, 10 elements per row. So that fits 10. And then down here is the F block. These guys are kind of, off on their own. The F block of the periodic table fits 14, and there's 14 elements across. Okay, so how can we use this to actually give the electronic configuration? This is going to be a little straightforward, and then it's going to get a little complicated, okay? Let's talk about hydrogen first. Hydrogen has 1 electron that we need to take into account. We need to give an address to that 1 electron. Well, hydrogen is right here. It is in the 1, because it's the first period. 1, it's in the S block, 1s, and that has 1 electron in it. So the full electronic configuration for hydrogen is 1s1. So far, so good. Helium. Helium has 2 electrons we have to take into account, or 2 electrons we have to give addresses for. So we have to go through hydrogen to get to helium. So here's helium. It's in the 1s, and there's 2 electrons. So its full electronic configuration is 1s2. Let's do beryllium. I'm going to get tougher. We're going to skip lithium. Let's go on to beryllium. Beryllium has 4 possible electrons. We have to give an address to all 4 of those. Now, we are trying to get here. We have to go through hydrogen. That's 1s1. We have to go through helium. That's 1s2. We're going to come over here. Okay, we're done with that row. Now we're going to come down here to row 2. 2s1 would be lithium. 2s2 gets us to beryllium. So the full electronic configuration for beryllium is 1s2. 2s2. You just keep filling in as you go. Okay, let's do a tougher one. I'm going to get tougher right away. Let's go ahead and do phosphorus. Here's phosphorus. We got to go through everything to get there. So we have to do a total of 15 electrons. 1s2 gets us through to helium. 2s2 gets us to beryllium. We're going to keep following on over. We're still in the period 2, 2p, because we're in the p block. 1, 2, 3, 4, 5, 6. 2p6 gets us to neon. Come on down here. Now we're in the group 3, period 3. 3s2 gets us to magnesium. Follow it straight on over. 3p, because we're back in the p block. 3p, 1, 2, 3, 3p3 gets us over to phosphorus. How do you know if you've done it right? It said we had to get to 15 electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. We've accounted for every one of those 15 electrons. So you just keep following along. You just keep doing what the periodic table tells you to do. As long as you remember S, P, and D, and really I'm not going to ask you any F's, S, P, and D's, you can keep filling it up as you go. All right, let's do another example. So again, I'm going to highlight this for now. This is my purple. This is my S block of the periodic table. Green was P. I used this color instead. And blue was D. And again, I'm not really going to worry about the F's because I don't usually ask about the F's. And the reason I don't ask about the F's is because there's more exceptions to the rules. And I don't actually really like giving you guys exceptions to the rules, so I don't really talk about the F's. So there's our S, P, and D block of our elements of the periodic table. All right, so let's do the full electronic configuration for calcium. So again, I'm going to take a second here. I want you guys to pause the video and give it a try yourself, right? Like, I can do this all day long. I have a PhD in chemistry. This is not hard for me. I want you guys to take the time and try to figure out yourself how to do this. So pause here, look up some other videos, look in your book, see if you can figure out how to get the full electronic configuration for calcium on your own before you watch me do it. All right, hopefully you've paused. So I want to do calcium. Calcium is going to have a total of 20 electrons. I've got to fill in all 20 of those electrons as I go. I'm going to do this with a highlighter so you guys can really see. So I'm going to fill in from hydrogen to helium. That's 1s2. You guys are going to quickly learn that this gets really, really repetitive. Now I keep going. There's nothing over here, so I just come down here to this group, or this period of the periodic table. This is going to be 2s2, gets me to beryllium. Keep on trucking. I run in over here. This is 2p, 1, 2, 3, 4, 5, 6. 2p6 gets me on over to neon. Got to keep going. Come down here. This is group period 3. 3s2 gets me to magnesium. Keep on trucking. I run into aluminum, which is in the 3p block. 3p6. 1, 2, 3, 4, 5, 6 gets me over to argon. I got to keep on trucking. Down here to the 4th period of the periodic table. 4p2. I'm so sorry. 4s. 4s2. gets me to calcium. Again, double check, make sure that you've accounted for all of them. 2 and 2 is 4, 10, 12, 18, and 20 electrons. So I have accounted for all of the electrons in calcium. All right. So far, so good. Let's do a harder one. My mouse is about to run out of power. This is a good time here. I'm going to highlight these guys again. We've got purple and green and blue, SPD, helium goes over here. 1, 2, 3, 4, 5. Now I'm going to get tough. All right, I'm going to jump right up in difficulty. I'm going to tell you how to do what happens with the D's. I haven't actually given you one with the D block yet. So let's do one. Let's do a tough one. Let's do palladium. Yeah, I want to do palladium. 46. We got to get all the way to palladium. Now, the thing I'm going to tell you before you try this on your own, the D's are out of order. The way our periodic table is drawn is really, it's not quite accurate. That's why we have this F block like kind of hanging out on the bottom. Things are a little bit weird. And due to some quantum mechanical issues, this is not the 4D. This first guy here, scandium, is not in the 4D. It is actually the 3D. The D's are out of order. The 3D fills after the 4S. The 4D, here with yttrium, fills after the 5S. So you need to remember that the D's do not just follow the period number. The D's are out of order. All right, so we're going to do palladium. I'm going to start at the beginning, and I'm just going to keep working through until I get to where my palladium is. So 1s2 to helium, 2s2 to beryllium, 2p6 to neon, 3s2 to magnesium, 3p6 to argon, 4s2 to calcium. Be careful. The D's are out of order. 3D10 gets us to zinc. Remember, D has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D10 gets you to zinc. Then we're back on track. 4P6. 4P6 gets us to krypton. 5s2 gets us over to strontium. 4D, 1, 2, 3, 4, 5, 6, 7, 8 gets us to palladium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d8. The D's are out of order. Be careful. Let's do one more. I'll do a pause for you guys on one more of them. Let us get to bromine. So I want the full electronic configuration for a bromine atom. So again, if I were you, I'd pause the video. Take out your periodic tables. Try to figure it out on your own, because, as much as it would be nice for you guys if I could take your exams for you, I can't. So I strongly recommend that you give this a try on your own, because you're going to be all alone when you take the exam. So while I'm drawing in here, you can pause it up. Like I said, I know how to do this. I'm a chemistry professor. I know how to do this. You guys need to figure it out and learn on your own. All right, I'm going to get to bromine. Full electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The D's are out of order. So 4s2 got me here to calcium. I'm going into the D block of the periodic table. The D's are out of order, so I'm going to go 3D. 10 gets me over to zinc. Back to normal. 4p, 1, 2, 3, 4, 5. 4p5 gets me over to bromine. All right. Now, we can do the shorthand electronic configuration for bromine. That's the full electronic configuration. 1s2, 2s2, starting all the way at hydrogen, I'm sorry. The full electronic configuration for bromine is all of that. But we can do the shorthand electronic configuration as well. For the shorthand electronic configuration, you start at the nearest noble gas that comes before. Let me write that down. You start, this is the shorthand electronic configuration. You start at the nearest noble gas that comes before. So here we're trying to start with bromine. The noble gases are the group 8s, so these guys here are the noble gases. So the nearest noble gas that comes before is argon. So we're going to cut this down. We're going to put argon in these square brackets. And then we just continue on like normal. So if we start from argon and we come down here, 4s2 gets us to calcium. 3d10 gets us over to zinc. And then 4p5 gets me to bromine. So it's like all of these things. Let me use yellow here. All of these are now included in what we just put in the square brackets for argon. So that's the shorthand electronic configuration. The nearest noble gas that comes before, and then you continue on after that. I think I'm going to stop here. I think that this is enough information for today. And hopefully I will be back and see you guys on Wednesday, and we will pick up here with full electronic configuration and shorthand electronic configuration.